Greetings from Microlab Northwest. You know, we were talking about light, and the first model that we used for a transverse wave, which is what light is, was a rope attached to some anchor point. When we moved the rope up and down, we created a wave that moved toward the anchor. If instead we move the rope in all kinds of different directions, it's no longer a nice transverse wave. We see the rope moving in all kinds of directions as it moves toward the anchor point. What if we put a picket fence between us and the anchor point? As we move the rope in all kinds of directions, some of the energy that was not just up and down is going to be lost as the rope travels through the picket fence. So the light, well, in this case, the rope wave that travels through that picket fence is going to be forced into primarily one direction, up and down, parallel to the staves in the picket fence. That effect is called polarization. They weren't familiar with the concept of polarization back at the time of Snell and of Huygens. They understood that there was a particular property called the refractive index of a material that could be used to characterize the material. But when Erasmus Bartholinus came along and said Snell was wrong and used a calcite crystal to demonstrate that, there was a need for another model. That other model we'll take a look at today. It has to do with polarization, just like the picket fence that was used to normalize the movement of the transverse wave of the rope traveling toward the anchor point. So let's take a look at that. Here's a calcite crystal similar to what Erasmus Bartholinus used. Now, if we put a mark on one side of the calcite crystal, we have a single mark. If we look at that mark by looking through the calcite crystal, we see two marks. That was what caused Bartholinus to say Snell was wrong. So how do we resolve this issue? Snell looked at this problem and he said, it's clear. The ethers through which the wave travels, it has a different density depending upon how the light travels through the ethers. Well, we started with one mark. We ended up with two marks when we looked through the crystal. We don't end up with a whole bunch of marks, just two. So the material must have two paths that the light takes as it travels through the crystal. Two and only two. That's an interesting property all by itself. But how do we distinguish between the two? When we are looking at the mark through the crystal, there must be a difference in how the transverse wave is oriented. Otherwise, we'd only have one mark. If we look at the crystal carefully, we can see that one of the mark appears higher than the other one. That tells us that the refractive indices along the path that the beam is taking is different for each of the two paths. One material is higher than the other, and we can certainly tell that by, as we move our position of view, we can see one of the object is moving more as we change our position than the other one. That's just like if you take your fingers, put one lined up on the other, use one eye, and as you move your head, you'll see the finger that's closer to you appears to move more than the finger that's behind it. We have the same thing with the calcite crystal. When we wanted to determine a particular path for the transverse wave, with the rope, what we did is ran it through a picket fence. Well, there is an optical picket fence, and that's called a polarizing filter. Now, the polarizing filter that we're looking at here, of course, is a relatively new invention, but there are other polarizing ways of making polarized light that we'll talk about briefly later that provided the information that people needed. It took a couple hundred years for that to actually be resolved. Huygens said that the ether was different. As a matter of fact, he even measured how much different the two ethers were. In other words, what the difference in electron density was along the two paths. He didn't know it was electron density. He just said it was different densities of the ether. Well, if we take our polarizing filter and we look at the two images coming through the calcite crystal, we notice that as we rotate the polarizing filter, we see one image and then we see the other. And at the position in between, we still see both images. So in one position, we see both images. If we rotate 45 degrees, we see only one image. And then if we rotate 90 degrees in the same direction, from that image, we see the other image. So these two images are linearly polarized beams. And our linear polarizing filter allows us to select one image or the other image. And at the position in between, we get both images. So that's useful. That tells us that we can actually measure the relative refractive index of each of the paths through the calcite crystal. That was the beginning of optical crystallography. Now, there are lots of things that we can learn by looking at different materials with a polarizing filter. A lot of the images that you see taken through the microscope that are so colorful, are actually using polarized light with different minerals or different substances that allow you to see both paths. But the paths, when they come through the polarizing filter, are caused to interfere with one another. When they interfere with one another, they create colors. And that's where we see the colors when polarized light is used. Now, in order to see the multiple colors that you see quite often in these photographs, you need two polarizing filters. You need one polarizing filter below the object and another polarizing filter at right angles to that above the object. In the microscope, that's done by having a polarizing filter on the base of the scope, and then there is a built-in polarizing filter in the polarizing intermediate tube that is always present in a polarized light microscope. The polarizer at the bottom, polarizing filter at the bottom of the scope, is referred to as the polarizer. And the polarizing filter in the polarizing intermediate tube is referred to as the analyzer. Now this leads to all kinds of interesting measurements that we can make, interesting determinations of the properties of a crystal that is only possible because of polarization. And so we'll see some examples of that. We'll see how we can get some very colorful effects, but more importantly, we'll find out what those color effects actually signify. So for right now, that's just a brief introduction to polarized light. We'll see a lot more of the effects of polarization on materials as we continue this series talking about how light interacts with matter. One of the interesting things that we have discussed is the fact that all of this is the result of the electron clouds that are distinctive in each material. Each material has its own unique electron cloud. In some materials, the electron cloud has a specific structure to it, having denser electrons in one path than in the other path. So we'll look at that. There are actually 3 different patterns that you can have for that electron path through a crystal. We'll see some examples of that too. Right now, let's go ahead and end our discussion at this point, and we'll come back and get into the next step a little later. Have a good day, and so long for now.